Today we're going to talk about section 2.8. One-to-one functions and their inverses. We've already gone over the definition for function, which includes the phrase for every x input, there is one and only one output. So for every x, there's one and only one y, or for every input, there's one and only one output. Okay, we said that we could graphically check this by using the vertical line test or vertical bar test. Now, we know a vertical line or a vertical bar has an equation of x equals a. So this would be a vertical line. So this would cross the x-axis. This is the x-axis and this is the y-axis, right? It would cross the x-axis at 3. So the name of this line, vertical line, would be x equals 3. Now, if I were to have a picture now to indicate whether it's a function or not, so if I had something that looked like this, if I draw a vertical line somewhere on this graph and it touches in more than one spot, then I know that it's not a function because this is an x equals 3 if you will, and then it would have two y values. So for every x, there's one and only one y. So this would be not a function. If I gave you one that looked like this, again, here's my x and y axis, and my picture looks something like that. Then for every x that I draw a vertical line, it only touches in one spot each time. So this one would be a function. Now we already know how to do a function. Like I said, for every x there's one and only one y. For every input there's one and only one output. So graphically we're now going to look at what we call a one-to-one function. So our section says one-to-one functions. So that must be something different than just being a function. The one-to-one function says for every x there's only one y, but it also says the reverse of that. For every y there's only one x. So we have the first part. For every x there is one and only one y, but now one-to-one function adds the extra part that says for every y there is only one So you're going both ways now. So this is to be a one-to-one function. So for every x there's one and only one y means that we have a vertical line or vertical bar test. For every y there's only one x means that we must have a horizontal line test. So for it to be considered to be one-to-one, both of these things have to be true. So that means it has to pass the vertical line test and it also has to pass the horizontal line test. So let's see if we can find a one-to-one. Okay, so we're looking to see a one-to-one function. So if I give you a picture that looks like this, first, is it a function? Okay, so does it pass the vertical line test? So I have yes, passes the vertical line test. It only touches in one spot. But does it pass the horizontal line test? So if I draw a horizontal line, it touches in more than one spot. So this one is a function, but not a one-to-one. So not one-to-one. Notice the indication here, I just made an abbreviation 1-1. So that means the same thing as one-to-one. All right, let's try another one. So if I give you a picture that looks like this, is that going to be one-to-one? Well, vertical bar test passes the vertical bar test, but does it pass the horizontal bar test? So in this case, this one is yes, it is one-to-one. Okay, I'm going to give you another one to try. One-to-one or not one-to-one? Okay, so it passes the vertical, but does it pass the horizontal? No. So here it touches in two spots. So this would be not one-to-one. So everybody okay with the one-to-one? All right, so another way that we can look at one-to-one functions is if we're given f of x equals x squared. Now the first thing we know is that this is a what kind of picture? Yes, it's going to be a parabola. We know that this is a positive 1 in the front, so what does the parabola do? Well, the parabola opens upward because we know that this is a positive 1 and it's on the x squared. So if it opens upward like that, then we know it's a function, but we also know it's not one-to-one because it touches in two spots on the horizontal bar test. So what a lot of times that they do is they restrict the domain to make it into a one-to-one function. So if I were to take this same parabola and only take part of the parabola, then we would have one-to-one. So if I make just this part, then my restriction of the domain would be what? All the x's that are from 0 going to the right. So this would be x has to be greater than or equal to 0 to have a one-to-one function. Okay, the next thing we're going to look at is an example. Again, we're still talking about one-to-one functions. We're going to use an idea that if f of x sub 1 equals f of x sub 2, then x sub 1 equals x sub 2, to show the function to be one-to-one. If the y's are equal to each other, then the x's are equal to each other. Okay, so if I have f of x equal to 3x plus 4, and I want to show that that is one-to-one, then we're going to say 3x sub 1, because we're plugging into here, plus 4, we're plugging into that, f of sub 1, and we have 3x sub 2 plus 4. So that's the f of x sub 1 and f of x sub 2 we plugged into the input. Here's my input. So I'm going to subtract 4 from both sides. 3x sub 1 equals 3x sub 2, and divide by 3 on both sides. So I get x sub 1 equals x sub 2. So we said that if we know that this is true, then the function is one-to-one. So we've just shown that f of x sub 1 equals f of x sub 2 leads us to x sub 1 equals x sub 2. So it is one-to-one. Now we're going to look at the inverse of a function. So in order for it to have an inverse, the first thing is let f of x be a one-to-one function. With domain A and range B. So A is my input, domain is the input, and B is my range, the output. Then it's f to the negative 1 of x inverse function. So that's what this f to the negative x stands for, inverse function. Has domain B and range A. So f inverse of y equals x means f of x equals y. Now, the inverse switches the x and the y. You can see here was the y before, now it's the x. So the inverse switches the x and the y's. So if I give you an example of inverses, I'm going to start out to find the inverse of the function. So an example, I'm given f of x equals 3x plus 4. and I want you to find the inverse of this function. So the first thing we're going to do is rewrite f of x as a y. Now we said that the inverse function switches the x and the y, so now we're going to switch the x and the y. So the first thing we did was set f of x equal to y. The second thing we're going to do is switch the x and the y. So now this becomes x equals 3y plus 4. So first thing we do, f of x equals y. Second one, we switch the x's and the y's. The third one is to solve for y now. So I subtract 4 to both sides. I get x minus 4 equals 3y. Divide by 3. 3's cancel, and I get y equals x minus 4 over 3. And then this becomes f inverse of x equals x minus 4 over 3. So this was my original function, and this is my inverse function. So what do? We set the f of x equal to y. We switch the x's and the y's, and then we solve for y, and that finds the inverse function for us. Now, one of the things that we can do to show that two things are inverses of each other is to do what we call the composition function. So we're going to write these two functions down first and prove to you that our answer is correct. So we've got f of x equals 3x plus 4, and we've got f inverse of x equals x minus 4 over 3. Now, what I'm going to do first, though, is I'm going to rename this as g of x. So we're trying to show that f of x and g of x are inverse of each other. So show f of x and g of x are inverses. Now, you know they're inverses because you just found them to be inverses. But to show that they're inverses, you have to show that f of g of x, the composition function, and g of f of x both come out to be x. So to show that they're inverses of each other, then you have to do this composition function and show that both of them come out to be x. So we're going to start with the first one, f of g of x. So this is g of x. So I'm putting that in for g of x, and I get f of x minus 4 over 3. But now this is the input into f, so I have to plug it in for the input onto f. So this is going to be 3 times x minus 4 over 3 plus 4. So when I multiply the 3's cancel out, and I get x minus 4 plus 4. These add to be 0, so I get x. So that's a good thing because we wanted it to come out to be x. So now we've got to do the other way. G of f of x. So now we're going to solve and plug in f of x. So f of x is my 3x plus 4. So I've got g of 3x plus 4. Then what do we do with this? We take 3x plus 4 and we put it into g. So I've got 3x plus 4 minus 4 over 3, because we're plugging into the x. So now these parentheses can be associative, so you can take and put the parentheses over here. So the 4 and the minus 4 is going to cancel out, and I get 3x over 3. But now the 3's can cancel out, and I get x. So since I've shown the two compositions both come out to be x, I know that these are inverses. Now again, we knew they were inverses because we made them to be inverses when we started out. So this is to show that they're inverses, and then the other way was to actually create an inverse. All right, we're going to try another one where we're going to write the inverse of the function. So find the inverse of the function. So we start out with f of x equals x to the fifth minus 3 over 2. So that's the function that we're going to find the inverse of. So what did we say to do first? The first step was to get f of x equaling to y. So we're going to have y equals x to the fifth minus 3 over 2. So we're changing f of x into y. The next step we said was to switch the x and the y. So this becomes x equals y to the fifth minus 3 over 2. And then we said to solve for y. So to solve for y, I'm first going to start out by multiplying by 2 on both sides. So the 2's cancel on this side, and I get 2x equals y to the fifth minus 3. I'm going to add 3 to both sides. So I get 2x plus 3 equals y to the fifth. But I'm solving for y, so I'm going to take the fifth root on both sides. So this gives me y equals the fifth root of 2x plus 3, and that would be my inverse then. So f inverse of x equals the fifth root of 2x plus 3. So we're finding the inverse function of this original function. Give everybody a chance to catch up to that point first. Okay, the next one we're going to find is the inverse of a rational function. So find the inverse of a rational function. Now, what makes something a rational function? Rational ratio, so we're going to have something that looks like a fraction then, right? So we have f of x equaling 2x plus 3 over x minus 1. So we want to find the inverse, so we still follow those steps. The first step is to let f of x equal y. So we get y equals 2x plus 3 over x minus 1. The next step we said was to switch x and y. So we get x equals 2y plus 3 over y minus 1. So now we're solving for y is the third step. So these are the 3 steps we've been doing for finding the inverse of a function. So on this one, we're going to put this over 1 and cross product. So when I cross product, I get x times y minus 1 equals 1 times 2y plus 3. So we know we can do cross product when we have the equality of 2 ratios. So we're going to do distributive property, x, y minus x equals 2y plus 3. We're solving for y, so we want to get all the y's on one side. So we're going to bring the minus 2y to this side and the plus x to that side. So these cancel out, and I get xy minus 2y equals x plus 3. So hold on to that for a second, give everybody a chance to catch up. We're solving for y. So what do you see in common to these two terms? You see a y, so we're going to distribute out a y and get x minus 2 equals x plus 3. This is multiplication between that y and that term, so what are we going to do? We're going to divide both sides by x minus 2. So I get y equals x plus 3 over x minus 2, which now would be my inverse function. Negative f of x equals x plus 3 over x minus 2. So f to the negative 1 of x, the inverse function. Okay, the last thing we're going to do is a quick application problem. This one is example 11 on page 225, if you want to look it up later in your text. So I'm going to give you the general gist of it and then you can look it up. At a pizza restaurant, the daily special for cheese only was $12, plus $2 for each extra topping. Set up a function of the price of a pizza with n toppings. Okay, so the first thing we're going to look at is the basic cheese pizza is $12. Then it says that it costs $2 for each extra topping. So I guess they're counting cheese as a first topping then, right? So the first thing it wants us to do is set up a function for the price of the pizza. And it says with n toppings. So for each extra topping, it's going to cost $2. But we just get the cheese pizza by itself, it's going to be $12. So the price in relationship to the number of the toppings, so that's what P of n is going to be. Price of the pizza, you want the price of the pizza with n toppings. So this is going to be price with respect to n. So that means we're going to have to pay the $12 for the cheese pizza plus $2 for each extra topping. So n is the number of extra toppings. See what it says, n is toppings. So we're going to have 2n. Now we're going to solve this for n and then decide what that means. Now, to make this life easier without using this right here, we're just going to write price equals 12 plus 2n. So now we're going to solve for n. So to solve for n, I'm going to get n by itself by minus 12. So I get price minus 12 equals 2n. And divide by 2, divide by 2. So I get n equals price minus 12 divided by 2. So what does this stand for? What does it actually mean? This says that it gives us the number of toppings if you know the price. So if I know that my price of my pizza is $50, then I can put P as 50, and then that tells me how many toppings I'm going to get. So the question's going to say, how many toppings does a pizza that costs $22 have? So what did we say we're going to do with the $22? We said we're going to plug the 22 in for the price. So we get n equals 22 minus 12 over 2. This gives me 10 over 2, which gives me 5. So my number of toppings that I have is 5. Thank you.